This is Paolo Lino from Technical University of Bari, Italy. I'm the chair of this session titled Automotive, related to applications of modeling and control for automotive systems. We have 5 presentations. I recall to each of the speakers that we have 15 minutes and then we will have 5 minutes at the end of each presentation for the questions. So let's go for with the first presentation. Let me introduce Francesco Crocetti, who is going to present the work titled a data-driven sleep estimation approach for effective braking control under varying road conditions. So please.
Hi everyone, my name is Francesco Crocetti, and today I introduce the work which my co-authors and I developed as a part of a European project called eBrake. So the eBrake project is basically focused on developing a new type of electronic brakes for a new generation of aircraft, and inspired by this project, we focus our attention to the tire rod friction estimation problem, of course, for an aircraft enduring braking maneuver. That's because this is a shared challenge for all the braking control systems, and additionally, the friction estimation become critical during 2 main situations. The first one is the braking phase after landing, and the second one is the rejected takeoff scenario, where the airplane must stop the takeoff procedure at high speed. So to define our problem, first we pay attention to the friction model. In fact, in the literature, the wheel friction model assumes that the longitudinal tire force is given by the product of 2 main components, a nonlinear function mu lambda and a vertical force Fg acting on the center of the wheel. So for the sake of the estimation task, the tire model can be simplified starting from 2 main hypotheses. The first one is that during the braking maneuver, the motion of the airplane occurs along a straight line, which has the same direction of the runway. And then usually the brakes are located on the real wheels of the airplane, and so there is no direct steering. Generally, the function mu lambda represents a nonlinear lumped model for all the phenomena characterizing the actual road type friction. And in particular, in this case, we use the Burkhardt friction model, and which depends on the variable lambda, which is the longitudinal slip value, and which is parameterized by 3 different betas. And usually the Burkhardt friction model describes 4 different road conditions: dry, wet, cobblestone, and snow. And finally, to define our problem, we also used the quarter car model, just because for the sake of the estimation problem. We used the quarter car model to model the aircraft's dynamic during the braking phase. And referring to the Burkhardt friction model, we also define the longitudinal slip, which is a variable that is bounded usually between 2 values, 0 and 1. 0 means there is no slip, and 1 means that the wheel is locked. And it depends on 2 main speed measurements: the aircraft speed and the wheel speed, coming, of course, from the aircraft sensors. So remembering the shapes of the Burkhardt curves, we define, which have a local maximum, we define the optimal friction value, which is the maximum value for a given friction curve, and the optimal slip value, which is the associated slip value. So we wanted to design a real-time algorithm yielding the estimate of the lambda star, which is the optimal slip, using the measurements to the main velocities, the aircraft speed with respect to the ground, and the wheel speed. And of course, the obtained value can be used as a set point for the braking controller in a closed loop scenario. And to do that, we use this estimation scheme where the core of the estimation block is an artificial neural network, in particular the multi-layer perceptron regressor. And we collect during a real-time operation set of pairs lambda mu and collected during braking operations. And this is possible by the knowledge of the two speed values coming from the aircraft sensor and by performing a model inversion. And the idea is that if the relationship between lambda mu pairs and the surface, which is unknown, can be captured, it's reasonable to extend the estimation function to predict the optimal slip directly. And of course, the availability of the optimal slip estimates allow us to benefit from the slip controller scheme. In fact, using the predicted value of the best slip coefficient can be used as a set point for the controllers. In this case, we analyzed two different regulators, the PI regulator and the sliding mode controller. The aim of this regulator is first to limit the braking effort requested by the pilot, and then to keep the slip value to the set point, which is the lambda star coming from the MLP. Of course, since we used an artificial neural network, in particular the multi-layer perceptron regressor, it must be trained in a supervised manner. So to build a suitable dataset for the MLP, we defined and sampled a three-dimensional space which we call the Burkhardt friction cube, built from the Burkhardt model and its spanning values of betas. And of course, we added some Gaussian noise just to model the noise coming from the speed sensor of the aircraft, and the obtained dataset is split into 4 different subsets: training, validation, hidden, and reference. Just to assess the benefit of this setup, this configuration, we performed 3 different sets of tests. The first one is the dataset-based test, which is basically a quantitative evaluations of the performance achieved by MLP over the entire dataset by using the root mean square error scores. And we also define open loop and closed loop tests in a synthetic simulation environment and compare the results with another model-based and state-of-art strategy, the recursive least squares approach. Just to perform a more realistic experiments, we define for the real-time experiments a more realistic scenario where we simulated the braking phase of an aircraft over an unknown surface whose condition change during, of course, the braking operation. Talking about the first test, as mentioned before, this is a quantitative evaluation based on the root mean square error scores achieved by the MLP over the entire dataset and subset, training, validation, test, and reference. And it's possible to see from the table 1 that the obtained results show that the MLP estimator is able to generalize, since the test and reference set are excluded from the training phase, and also the reference dataset contains only the Burkhardt's default rows, wet, dry, cobblestone, and snow. And in this case, the overall performance for the test and the reference tests datasets are higher than the ones obtained for the training and the validation dataset. In general, the average error percentage achieved by the MLP is around 19%. And for time reasons, we report only the closed loop results. In this case, as first step, we qualitatively compare the time behavior of the estimates achieved by the MLP and the RLS approaches for both the sliding mode controller and the DPI controller. And of course, you can see two different road transitions, dry is not dry as not wet dry. And it's possible to, with green line, we have the real ground truth values of the best slip, and with brown and blue lines, the predicted value of the MLP and the recursive least squares approaches. And in general, we can say that the MLP achieves lower errors, and the road transitions don't compromise the performance, the overall performance. And it can also be observed that the performance obtained with the PI controller and the sliding mode controller are in general comparables. And conversely, if you take a look on the blue lines for dry snow, dry condition and snow wet dry transition, we can see that the recursive least squares approach is heavily affected by surface transition, and in most cases the estimates diverge and becomes unreadable. And to perform a deeper analysis of the overall performance, we also performed a quantitative evaluation as in the first test setup. But in addition to the root mean square error scores, we used two more metrics, which are the traveled distance and the braking time required to stop the aircraft. And again, we can see that the MLP outperform the recursive least squares approach in the most of cases, and even for the PI controller and for the sliding mode controller situation. And as an example, it's possible to notice that our approach can also improve the overall efficiency of the braking system and the braking maneuver. And as an example, for the snow, dry snow, and the snow, wet snow transitions, it's possible to see that the recursive least square approach requires up to 700 meters and 60 seconds more than the MLP to stop the aircraft. And just to wrap up, this work proposes a data-driven strategy to estimate the optimal slip value and to perform an efficient braking control. And we used an artificial neural network, in particular the MLP, that we proved that it can detect efficiently the road conditions by processing sequences of slip friction pairs. And the synthetic experiment results show also that the proposed approach achieves better performance, of course in a synthetic environment, achieves better performance when compared to the state-of-art recursive least square approach. Thank you for your attention, and if you have many questions, please contact me.
Thank you very much for your nice presentation. We finished a couple of minutes in advance than the scheduled time. So we have almost 6 or 7 minutes for questions. Is there anyone that wants to ask questions? So for now, no questions. I have one or a couple of questions. Can you hear me? Regarding the PI and the sliding mode controllers.
Yes.
Actually, you don't have a mathematical model of the system.
No, so, no, yes. Okay.
So the question is related to how to tune the controllers. And in particular, regarding the PI controllers, probably it has been used heuristic approach, trial and error approach.
Yes, yes, of course. So for the sliding mode controller, we used. Wait, I have to.
Yes,
okay.
How to
yes,
extraction of
okay. Yes.
And convergency to the
for yes, for example, for the sliding mode controller, we followed the approach used by Riccardo De Castro that used the sliding mode controller for the recursive least square strategy, and we left we used the same configuration that he used, and for the PI controller, as you told, we use an empirical method. That's because the idea is that we want to use this regressor and this approach as for an estimation test. So we want to use this approach like a smart sensor. So in this case, the controllers must be changeable. No, you know. And because the idea is that we want to isolate the estimation block to the controller's block, from essentially.
So not extreme extension for now regarding the controller performances.
No, yes, yes, of course. In future work, we'll of course analyze the impact of different configurations for the controllers. Because if you see here as an example, for example, the spikes comes from both the training phase, that doesn't matter the transitions, and of course the controller can of course improve or decrease the overall efficiency of the overall estimation, because they are connected basically.
I think we still don't have any questions, so we still have 3 minutes more for questions. So is there anyone that wants to ask? No. Probably I missed this, but are these experimental results or coming from the simulated model?
These results comes from the synthetic environment that we built from simulated.
The model.
Yes, okay, because it's very hard to get real data from aircraft.
I don't know if I can ask this question. Is this in this work done in cooperation with some company?
Yes, with Piaggio, which is okay.
Yes. So still no questions.
Sorry, Paolo.
Hello?
Yeah, I think someone is raising hands in the attendees. Elio Usai. I don't know if
I cannot see the hands. I wrote a message in the chat asking for anyone to write to book a slot for questions. I cannot see the hands. Maybe only Carla can see them.
Okay.
Okay, Elio Sai. Okay, I think we can activate Elio access for asking questions.
Give me a sec. Ok, c'è il solito minuto di ritardo.
Okay, I think that I can speak now.
Yes, so, I hear you.
My question was very similar to yours regarding the differences between the controller, since I almost see no difference between PI and sliding mode. So my question was, what is the sliding variable and what is the error signal for the PI? Because it's it's not strange that the two so much different controller have the so similar behavior. So that was my question and my doubt in the presentation. That was very similar to that of Lino.
Yes, I think we turned our PI controller to reach the same results with the sliding mode controller, but I think the results came from I think the environment simulation, because you know that the model is very simple, because we use the Porter car model, and we also use only a wide Gaussian noise for training the dataset. So we don't add some noise that probably can show better the difference between an approach with the sliding mode controller and the PI controller. And so basically it's the same. And of course, the initial brake effort requested by the pilot is kept equals and constant for all the simulation. Probably in a more detailed simulation and complex simulation where the braking effort requested by the pilot may change, probably we will see a stronger difference between the sliding mode controller and the PI controller. And of course, this is a synthetic simulation just to show the estimation capabilities of this approach.
Yeah, I think that point to check should be the relative degree between the sliding variable and,
yes,
and the switching controller that could give rise to such kind of behavior. But this was my question, my doubt about that. Thank you.
You're welcome.
Okay, thank you. I think we can go for the second presentation, which is related to the work titled Fault-Tolerant and Switchable Slip Control Architecture in Four-Wheel Drive Electric Vehicles. And it will be presented by Gerardo Amato. So please, you can go. I kindly invite the attendees to book the opportunity to ask questions by writing inside the chat, the public chat. Okay.
Do you see the screen?
Not anymore. Okay.
Okay. Thank you all for joining the talk. I'm Gerardo Amato from the University of Roma Tor Vergata. With my PhD supervisor, the Professor Riccardo Marino, we present the work Fault-Tolerant and Switchable Slip Control Architecture in Four-Wheel Drive Electric Vehicles. This work is already available on the IEEE library in the proceedings of a Mediterranean Conference of Control and Automation, which will be virtually held next week in St. Raphael. Since some years, the electronics on board plays already a special role in market vehicles. Some driving systems like short rudder for park assistant or adaptive cruise control, lane keeping, or ABS, CSC are all systems which contribute making the driving assisted and safety. On a virtual timeline, starting from vehicles with mechanical parts electronically controlled, like the steering or the throttle, the electric powertrain moved ahead through the hybrid motors until other configuration with one or two action motors, for example. The technological edge in the automotive industry is reaching the configuration with the 4 independent electric wheel motors. They are so called because are exactly housed inside the wheel hub with its own independent powertrain control units couple, which is the configuration we considered in our design. Generally speaking, a fault-tolerant control design is placed in the frame of robust regulation problem. At system layer, the goal is to challenge with some actuators or sensor faults, CS disturbances. The problem of nominal performance saving during the failure is addressed sometimes by the actuator grouping, in which once a generic fault is notified, the controller arranges the driving forces to the residual LT control set, like in this case on the front axle. Several existing fault detection techniques are based on the loss of control effectiveness as fault indicator. A wrong characterization can lead so to missed detection or false alarm problems as surveyed in Dumont. Then estimation skills of control algorithm results are useful for this goal and can be usually exploited. Sometimes the fault is a state variable to be observed. Some others, like in Marino 6, the motor parameters identification is used to isolate the fault, which is asserted when that parameters, for example, the stator resistance, for example, which is out of acceptable bound, the parameter estimation. An attendant problem thus is the reconfiguration practice of vehicle trim due to the fault. In Cato, a solution for a switching mechanism for 2WD is patented for combustion vehicles, where the mechanical transmission from a central engine can optionally switch in different transmission states by connecting or disconnecting configurable reduction differential gears with electronically controlled switches. Then the idea behind our work is to exploit the intrinsic robustness of the fault-controlled wheels to implement two main features for the controller towards the preservation of the nominal torque balancing. The first is a quick fault detection and isolation capability, FDI, and two, an integrated smooth switching function, SS, from 4 in-wheel motors to 2 in-wheel motors cases once the fault is identified on the axle. Adaptation skills of the actuator layer are used to perform a sensor fusion approach as follows. The model considered for the control design contains the 3-order XYZ dynamics plus the 4-wheel speed dynamics omega with the forces modeled with the Pacheco magic formula. From the cooperation of the 4 in-wheel motors, 2 forces terms appear as PI controllers, respectively at the longitudinal speed equation Vx and at the yaw rate dynamics R, and are namely FL and FD, respectively longitudinal and differential driving forces contribution. The sensors in the system are 2 accelerometers to measure X and Y acceleration, a gyroscope for the yaw rate, and 4 encoders for the 4-wheel speeds. The proposed strategy is borrowed from the multi-layered architecture of Amato Marino 3, in which 2 additional links between the extreme layers branches forward the FDISS selectors for the fault detection task. The algorithm works as follows. At the lowest layer, the 4 independent actuator controllers work as the in-wheel motor controllers. Each individual slip controller produces 2 decoupled input currents, ESQ and ESD, to the rotating frame model of the wheel motor to control both the motor tracking of the slip lambda and the magnetic flux psi RD references. In Amato Marino 3 was already proved the slip control stability, so that the resulting electromagnetic torque TMIJ implements a PI loop on wheel speed dynamics, and at the same time by providing with the integral part the estimation of load torque acting on the wheel runtime in order to compensate it. The slip references are given by the motion controller MC at the intermediate layer, in which a slip decouple produces 4 lambda IJ star references with such an equalization of the 2 longitudinal and lateral force controller, respectively the PIs on Vx and R errors, depending also on a fault matrix F, which acts as an insertion matrix. At the motion planning layer, the algorithm works in two phases. The first phase is the FDI, fault detection and isolation, in which the fault is detected and isolated on the base of a sensor fusion. The difference between the measured acceleration vector beta and the vector of transferred load gamma is evaluated. Gamma is calculated from the mapping of individual estimated load torques on wheel through the estimated force vectoring and then the two acceleration resulting the estimated acceleration. Once the fault is detected, a mutual comparison between coaxial twin wheels lead to understand rapidly on what axle the fault is located. In this case, for example, by a mutual comparison between the rear load torque. The second phase then is triggered when the fault is detected and the smooth switching function work. The branched FDI SS selectors are generated as exponential signals. At first, the fault boolean fault flags FI acts as a sleep switching signal, so that the detected fault produces a zero index in the matrix where the fault is, while the corresponding control currents are switched off by the rho IJ selectors. Then the selected scheme for FDI tasks result quite fast due to the relevant rolling load transfer on coaxial wheels, so that the imbalance on coaxial wheels load can indicate a problem, as well as unexpected saturation or sleeping. The detection robustness is entrusted to the redundancy of decision-making flags. In fact, the three decision layers are related to three hierarchical AND gates based on global local variable, respectively. On the chassis layer, we are looking to the difference in acceleration vector measure and its estimate. On the actuator layer, we are looking only to comparison of wheel load estimate. Okay, an example, just an example. Some software errors could produce an fault flag on a wheel, which communicates the error to its twin with an FT out. Even if this could indicate the error occurrence, the fault event is not triggered if at the aggregate decision layer, the global fault detection flag is not agreed by all FI modules, thanks to the hierarchical ends. Then the decision, the fault decision is made distributed among the control set. The proposed control strategy is validated with a car sim simulation of a vehicle cruising at a constant speed on wet asphalt. We considered a generic mechanical fault designed as a sudden incoming loss of load on rear left wheel, which the motor should compensate. The fault produces a sigma scaling factor appearing on the wheel torque down to the 80% due to an angular or linear miscalibration, for example. The test is conceived to show the rapidity of intervention of the FDI and switching routines from 4 to 2 WD cases once the fault is isolated on the rear axle. The fault detection task every time looks at the difference between the measured acceleration vector, the blue one, and its estimate, the green one. These are two independent vector acceleration evaluations which must agree. At the beginning, they are aligned. So when the estimate acceleration vector goes out of an acceptable cone, an acceptable range around the measured one, it means that a fault occurred. In this short video, the blue vehicle, which is the real one, are cruising, while the green one represents only an estimation of the heading motion. At the fault occurrence, the estimation faults. And so the estimated vehicle heading moves sideways. This is because the faulted angle gamma green, the green one, is spanning in plus minus 90 degrees, while the measured vector beta, which is the real one, is inside only plus minus 30. Then the two vectors coincide again only when the system recognizes the actuator failure, like at the end of the video, and after it transfers all the powertrain on the front axle. Then the vehicle balancing is restored again at the end. Step by step, the algorithm works as follows. At first, the fault is detected when the acceleration vector estimation error crosses the 30 degrees. Then in the fault identification task, the modal ratio between coaxial load torques are pulled. When at least one ratio crosses the 50% or a wheel receives as input an F twin equal to 1, the fault is isolated on the axle. A last check is done on the acceleration vector angle beta to understand if the load imbalance is caused by a steering maneuver. In this case, there is not a steering maneuver, and then the fault is accepted. Finally, the SS signals are triggered at the same time on the twin rear wheels, rear left and rear right. Then the fault indicators are zeroed in the matrix, as well for the current parameters, so motor selectors, sorry. Thus, the rear slips, the rear currents, and the rear fluxes of the motors are zeroed. And then the motor torques are zeroed for the faulted wheels. The cooperative architecture allows to transfer transparently the control action from 4 to 2 WD, thanks to the integral contributions, without the need of reconfiguration. Well, the integral action then will find automatically the new operating condition so that the torque value of residual control set is augmented here for the front wheels in order to compensate the loss of the two actuators. Consequently, chassis motion tracking, viewed as the nominal performance target, is preserved without perceivable macroscopic effects. As you can see, there is a very small error. In conclusion, the work deals with failure detection and isolation in a four-wheel motor configuration with distributed and switchable architecture. The independent 4PI slip loops provide a cooperative chassis motion control and a distributed load torque estimation. A sensor fusion approach is used for fault detection by observing the difference between the measured vector acceleration and its estimate. Then the four estimated load torques at the motors are mutually compared so as to identify quickly a mechanical failure on the axle in less than 1 second, while the switching command is given in 0.1, namely under typical driver reaction time. The failure is shown to slightly affect the longitudinal speed and yaw rate, but the control is capable of quickly compensating it. A special work we consider extending the test to more complex maneuvers like a bending maneuver or an acceleration or braking, while the distributed wheel load estimation allows to depict the wheel curve shape by combining slip and torque informations. The auto configuration features could lead to interesting applications in the frame of autonomous or semi-autonomous driving. A load-based slip decoupling could be considered to improve the vehicle road grip in the case of a different torque balancing during a curve or during an acceleration. Finally, the switching on rest of routine can be implemented too when the estimator recognizes the fault end. These are the references you will find in the paper, and if you have a question, please ask or write me at this email address if you want. Thank you for your attention.
Thank you for your nice presentation. If you have any question, you can book for asking in the main chat. I think that no one asked any question till now. I think we have time just for one. Okay, just a curiosity regarding the model of the car sim model, the parameters of the car sim model. How did you set the parameters? And if there is the opportunity to perform some experimental testing.
Okay, we are considered just for sake of adaptation to the market, a subcompact vehicle in which the wheels are small for a subcompact city vehicle. And then the main feature of the controller is that the wheel torques are not based on the knowledge of wheel parameters. Then, because of the integral part in the controller, then we are considered these also for a further possibility to have an experiment. So to have parameters near to a possible experiment.
So actually, they are not directly derived from a real vehicle, existing commercial vehicle.
Yes, are realistic.
But from a specific passenger car, I meant.
Yes, if you want, the parameters are these. Let me. Do you see? Are really parameters of a commercial vehicle. So we have considered also for the load of the wheels and the in-wheel motors, and so the total mass is considered, and all the dimension are related to a vehicle, which is in this case a Ford is a subcompact vehicle.
Okay, thank you again.
Thank you.
And we can go to the third presentation, which will be given by Michele Tomaselli with my PhD students. And the work is titled Design and Proof of Concept Validation of the Common Rail Pressure Control using a Continuously Variable Transmission CVT. So you can go.
Tell me when you can see my screen. Oh, first of all, can you hear me?
Okay, you can start. Yes.
Okay, perfect. Okay, everybody, just a moment. I try to remove the bar. Okay, everybody. I'm Michele Tomaselli. I'm presenting our work in collaboration with my advisor, Professor Lino, and Professor Carbone. That is a design on the proof of concept validation of a common rail pressure control using a continuously variable transmission. Just an outline of what we are going to see. We will see a description of the system, then the design of both the controller that we develop in our simulation environment, then of course our simulation results. And after this point, we will see an initial proof of concept description of test bench that we built up last year to start our idea, and of course also the experimental results. First of all, we need to introduce ourselves to the common rail system. That is a well-known system that let me say improve the performance of the diesel engine since the beginning of his appearance on the market, and its main advantages is to allow a good control of the injected flow in the combustion engine. This is possible because of the pressure regulation in front of the injectors that with the control of the timing of the injection, as I said, allow the control of the quantity to be injected in the engine. Of course, the main advantages are the bad performance in terms of combustion and of course in terms of emission. The main problem that we want to handle in this project is the fact that the high pressure pump in the actual system is coupled with the internal combustion engine with a fixed transmission as per gear transmission ratio. And our idea is to decouple these two speeds by using a continuously variable transmission that you can see labeled as 10 here. Introducing this component, we have a problem that is the redundancy of the actuators compared with the controlled output that is just one, of course, the common rate pressure. So first of all, we built up a method to handle this problem. Our method was to define the goals that both actuators must achieve. The FMU control, that is the traditional one, a solenoid valve, must allow a fast, precise and decoupled from high pressure pump speed regulation, while the CVT should allow a reduction of the high pressure pump speed, of course, without causing any disturbance to the high pressure regulation. So to solve this problem and achieve these goals, we build up two control loops. One for the traditional solenoid valve, the FMU, that is controlled by using an adaptive approach that is able to decouple this control from the high pressure pump speed. And for the CVT, we used a fuzzy logic controller that was suitable to achieve our goal. And going deeper in the control load definition, first of all, we started from the solenoid valve control. We used, as I said, an adaptive approach, in particular a model reference adaptive controller that is based on the pressure dynamic equation in the common rail that, as well known from fluid dynamics, can be evaluated as the sum of the flow that comes from the air pressure valve and the flow that is injected in the combustion engine or goes through the as leakage through the injectors. By linearizing this equation, we are able to build up an estimator, linear estimator for this model, and using the Lyapunov approach, we can derive a control strategy for the current of the solenoid valve. As we can see, we can also include the speed of the high pressure pump in the I don't know if you can see the pointer of the mouse. Probably not.
Yes.
In any case, okay. By using this component in the control load of the current, we can include the high pressure pump. So the one of the goals that we defined previously was the decoupling from the high pressure pump, and this is exactly what happens with by using this control loop. Switching to the other control loop, the fuzzy controller. First of all, the fuzzy control design starts from of course, from the variable that are the input of the fuzzy controller, and let me say the rules as the fuzzy logic theory teaches, the rules that we want to implement inside the controller. So first of all, we designed the membership functions. Then we design the fuzzy control rules table. That is one, of course, designed according our goals that we want to achieve. We want to of course, we want to make a correlation between the CVT transmission ratio and the pump, the flow demand that must be achieved by the high pressure pump. And of course, we want also to be sure that the pressure in the common rail is not disturbed by this controller. So we have the desired flow as one input, and the error of the pressure regulation as a second input. And of course, by merging the membership functions and the fuzzy control rules table, we can define a rules surface, just to have a clear idea on how the fuzzy controller works. Then we perform some simulation. By using this approach, we used real WHTC driving cycle for heavy-duty vehicles, and in order to compare these results with the traditional system, we compare our system with a fuel metric unit control loop. The results that we are going to see are partially normalized to meet some company agreements. In particular, all the information that are related to the high pressure pump, in particular the high pressure pump speed and the power demand. Okay, first of all, we are interested in the tracking performance that must be the same of the traditional one. And we can see that this control system guarantee the same tracking performance of the traditional system. While the main goal that we want to achieve by introducing the high pressure pump, that is the reduction of the high pressure pump speed, is achieved. We can see by this chart that through all the cycle, we have a drastic reduction of the pump speed. We can see by this chart in this chart that the 90% of the pump speed values reached with the traditional topology range between the 36% and the 76% of the maximum value. That is the value that we use to normalize the speeds. While this range becomes 28 and 59 with the new topology. What does it mean? This means that the mechanical power that is necessary to drive the pump is of course lower compared with the traditional one. Then we start to build up a proof of concept of this idea because of the availability of the spare part on the market. This proof of concept is was built up on gear pump test bench with let me say a suitable CVT and with a simplified circuit that we can see in this scheme. In particular, we can see that the transmission is derived from the bike environment, is known as Novinci or Enviolo, while the pump is a gear pump is used in place of the high pressure pump. Then we tried to implement a control system on an Arduino Mega because of the performance of the board. We were able to use a PID controller, and with this simple controller, we were able to reach a good tracking performance, and that are seems to be very, very good, and oh, sorry, and these make us give us the possibility to continue our investigation on a real test bench, because as you can see in the conclusion, the future development that actually is already ongoing is the implement of this concept on a real common rail test bench with a real high pressure pump and also injectors. The presence of the injectors, of course, is important because it's let me say a real disturbance on the common rail pressure loop, control loop. So this work that I summarized in this presentation was also already presented in two conference, and the part, of course, this is the main topic of my PhD. So thank you for your attention. If you have any question, please don't hesitate. Maybe there is something in the chat.
Okay, thank you,
If I'm
Michele.
able to open.
Okay, are there any questions? If you have, you can write a message in the common chat.
Ah, okay.
So, not yet. Maybe it will be useful to better clarify what are the differences of this new topology with respect to the commercial one.
Yeah, maybe I can share again quickly the screen. Just a moment. Tell me again when you can see the screen.
And also to highlight that the main advantage is the reduction, sensible reduction of the power consumption.
Yeah. So if
fuel consumption.
Yeah, if you see again the screen, okay, the main difference is the presence of the is a continuously variable transmission. That is absolutely a new concept in a common rail application, because as I said before, the current common rail system uses a spur gear that has a fixed ratio, and these cause some let me say difficulties in the design phase of the high pressure pump, because the high pressure pump is has to follow all the operative point that are reached by the internal combustion engine. This means that the high pressure pump is forced to go at very high speed while it is not necessary, and these in general the speed of the air pressure pump is always oversized. This is a very big problem, because of course, if the high pressure pump speed is very high, we have of course too much flow demand, too much flow that comes from the pressure pump that must be partialized. This partialization can cause some cavitation problem. So first of all, a reduction of the air pressure pump speed can, let me say, simplify the design phase and the test phase of the high pressure pump. And maybe the most important thing is that the mechanical power that is necessary to drive the high pressure pump is strictly related to the high pressure pump speed, because of the internal friction and the fluidodynamics effect. So by reducing the high pressure pump speed, there are a lot of advantages. And this is one of the achievement of this work.
Okay, thank you. Probably now it's clear for those who are not familiar with the common rail systems. So thank you again. I think we can proceed.
Question for Tomaselli.
Okay.
The high pressure, to reduce the high pressure is linked to a fuel consumption reducing.
Also, yes, one of the effect of this is a reduction of the fuel used during the usage of the common rail system. This, of course, comes from the reduction of the mechanical power that is necessary to drive the high pressure pump, because at the end, all the power comes from the internal combustion engine. So, of course, if we reduce the, let me say, the total amount of the power that is required to the internal combustion engine, at the end we have also a reduction of the fuel consumption.
And you have also a reduction of recirculation, which is even related to use of pump power. So
yes, we have also, in the in some common rail system that uses the so-called PCV, that is a valve that is mounted directly on the rail. This valve is used to discharge the rail when, let me say, a fast decrease of pressure is needed. And this recirculation, as you say, is let me say, a bad effect, because the high pressure fuel comes with a very hot temperature in the tank that can cause other problem. So
you even have to use power of the pump to raise the pressure to the value.
Exactly.
The common rate. So
yeah.
Okay, I think we don't have. I hope it was the answer you were waiting for.
Yeah.
Otherwise, we can even discuss later.
Yeah, of course, feel free also to send me an email if you want. There is the email address. And thank you again for your attention.
Thank you. So the next presentation will be given by Agostino Marcello Mangini, who is from Polytechnic University of Bari. And is related to the work titled An Eco Route Planner for Heavy Duty Vehicles. So you can start.
Can you see my screen?
Yes.
Okay. Thank you, Paolo, for the presentation, and good afternoon to everyone. In my presentation, I will describe an approach to reduce fuel consumption for diesel EV duty vehicles. This topic was investigated in the European project OptiTrack, where an eco route planner was implemented. This work was developed in collaboration with Gianvito Difilippo and Professor Maria Pia Fanti. Let's start the presentation with the summary. Before I introduce the reason of the proposed approach and the objectives, then I will show the system architecture and will describe in detail the two main components of the architecture: the data management architecture and the cloud optimizer. Moreover, I will show a case study and the corresponding result. Finally, I draw the conclusion and future works. In recent years, large attention is given to the problem of reducing fuel consumption and pollutant emission. Current solutions to reduce energy consumption and emission are reserved to light-duty vehicles and electric vehicles. However, most vehicles are diesel heavy-duty vehicles, and the current solutions are not feasible for them. Moreover, due to the increasing of the road freight traffic, projections indicate that the total heavy-duty vehicles energy use and CO2 emission are expected to remain stable at the current level over the long term, whether no policy action is taken. So, for this reason, our activity research was centered in the definition and implementation of a cloud platform to optimize heavy-duty vehicles routes by employing additional information as road topography, altitude, slope, traffic condition, weather forecast. Optimization was used to minimize fuel consumption and consequently pollutant emission. The proposed cloud computing system works offline and real-time after it receives the emission from the management fleet company. The cloud system determines the optimal route that minimizes fuel consumption, improve the routing planning during the mission, facing critical situations as accidents or bad weather conditions. Moreover, cloud computing system is used on board to calibrate engine and powertrain parameters on the basis of the choice of the optimal route and velocity profiles. The cloud computing system was the objective of the European project OptiTrack. So now I will show the system architecture. The cloud platform architecture is composed by a set of software components that can be divided into main optimization modules that work in a coordinated fashion under the name of Global Optimizer. These two optimization modules are Cloud Optimizer and Onboard Optimizer. And in our research activity, we focus our attention on Cloud Optimizer. The Cloud Optimizer component performs the route planning optimization task. On the contrary, the cloud system data can be divided in three groups: external resource, traffic, weather, maps, and topography, in green in the architecture, mission-related data, waypoint, payload, driver, maximum arrival time loaded by fleet management company, and real-time data, track position, speed, consumption, and real slope. Now we describe in detail the activity of the data management architecture that is one of the main blocks of the architecture. The data management works with the big data from external sources and real time from the tracks. The main components forming the data management architecture are data storage components in yellow, and it is necessary to collect all the raw data from external sources and tracks, and the business intelligent logic component in blue to integrate and fuse the data set. Among the data storage components, service data storage is responsible for the storage of input data from external sources and mission data from different data sources: topography data, ADAS data, for example, traffic forecasting data, weather forecasting data, mission and track data. And then the planning data storage that is responsible for the storage of the output data as the computed best route and the data from the track. On the contrary, the intelligent logic components includes two main subcomponents: planning data manager that manages the data flow and the communication with the track, and service data manager that retrieves data from external services, stores them to the data storage components in order to guarantee to have always the most recent data available. Now we present in detail the Cloud Optimizer, the focus of this presentation, and the steps to calculate the eco route and the velocity and gear profile. Cloud Optimizer components determines the optimal route of the truck in order to reach the destination by minimizing the fuel consumption and optimizing the route velocity profile. It is subdivided in 3 subcomponents that we'll detail in the next slides. Route network selector, this one, velocity and gear profile calculator, this one, and the route optimizer, this one. Sorry, route optimizer and the velocity and gear profile calculator. So, the operational activity of the cloud optimizer is described in 2 different scenarios. In pre-emission phase, the system calculates the eco-route, optimizes the velocity and gear profile, and sends them to the truck before the emission begins. In the emission phase, the eco-route is monitored by real-time traffic and weather data collection. If an accident or severe slowdowns occur, the cloud optimizer recalculates the best route and/or the velocity profile. As said previously, the cloud optimizer is formed of 3 components. The route network selector builds the route graph network, collecting the main possible routes from the origin to the destination. In this graph, the nodes are represented by geographical coordinates that identify road crossings. Velocity and gear profile calculator, on the contrary, integrates predictive traffic, weather condition, road topography, including slope and curve radius, on the basis of a simplified vehicle longitudinal model, and builds a weighted direct graph. In this graph, the nodes identify admissible velocity and gear. Finally, the route optimizer determines the optimal eco-route, minimizing the fuel consumption by employing the built weighted direct graph and using the Dijkstra algorithm. So, the route network selector works in 3 steps. Before, the route network selector selects by the maps data the fastest route R1 from the departure to this destination by passing from the waypoint respecting the emission duration time. After other M-1 network routes are selected connecting each crossing road in R1 to next waypoint and not completely coinciding with R1. Then the set of M routes is converted in a direct graph G, where the nodes identify crossings and the arc identify roads. It is necessary using an algorithm for the conversion because the road overlaps have to be deleted. Now, the velocity and gear profile calculator. It analyzes each road of G subdivided in about 200 meters apart points. In particular, the velocity and the gear profile calculator determines the admissible velocity and gear profile for each road, considering ADAS data, mainly slopes, curvatures, road limit, traffic and weather condition, and the payload. To this aim, the VGP calculator needs a simplified vehicle longitudinal model to quantify the fuel consumption and travel time between 2 points on the basis of the truck velocity and gear. Simplified because the calculation times have to be limited. We used the longitudinal model introduced by Elstrom. Finally, the route optimizer determines the value of beta and the minimum path of the weighted graph G prime by applying the Dijkstra algorithm. in fact, the road is converted in a graph where the nodes identify a pair of velocity and gear of a point situated in a specific coordinates, and the edge weight is given by a function depending by fuel consumption and travel time. I come back to this slide, and you can see the weight that depends by the fuel consumption MF and the travel time T. And beta is used to give more importance to the fuel consumption or to the time. And so for this one is important for the arrival time. So the emission phase starts when the truck begins its transportation mission. Since changes in traffic and weather condition can make the eco route not efficient, the eco route is monitored every 5 minutes. New data are considered in this case: truck GPS coordinates, presence of accidents, congestion, bad weather condition. Moreover, the network is not fully calculated in this case, in the emission phase, but only a mini network is determined in the vicinity of the accidents, using the crossing before and after the accidents. Now we show the case study. The validation was based on 2 models of Ford truck. One truck, the demo truck, was assisted by the eco-route planner. One truck, the base truck, was not supported by the eco-route planner. The demo was a mission from Golkuk in Turkey to Piacenza, passing from the waypoints Igoumenitsa and Bari. In the pre-mission phase, the route network and the route calculation was performed in 20 minutes. And in white, you can see the network, and in green, the eco route that derives by the optimization with the Dijkstra algorithm. And during the mission, the demo mission, an accident occurred in near Bari, and the emission procedure was activated by the eco-route planner. And so you can see the mini network and the eco-route that were calculated in 3 minutes. These one are the final results of the demo. The fuel consumption was normalized in kilometers, and the total fuel saving percentage was minus 10.8%. So, in conclusion, this paper presents a cloud computing system to support the fleet management company in the choice of the routes to be performed by heavy-duty vehicles. The cloud computing system is presented, its architecture, and how the best route and the optimal velocity profile are determined. Then a demo showed the efficiency of the proposed architecture, comparing a base truck with a demo truck equipped by the eco-route planner. The fuel consumption was reduced by about 11%. And finally, future works will design the onboard system that will collaborate with the cloud computing system to improve the efficiency of the proposed architecture. Then the onboard system can improve the truck powertrain parameters based on the best route in order to obtain an additional reduction of fuel consumption. Thank you for your attention.
Thank you, Agostino, for your nice presentation. I think we have time for one question. If you have any, please book it by writing a message in the comment chat. I cannot see any message yet. Just one question, which is related to the planned experimental tests. Do you have any notice about it?
A possibility was to create a simulation in order to obtain the advantage of the eco-route planner with respect a driver that that performs the mission. But in the project, this possibility is was not good because it was difficult to represent the behavior of the drivers. So we have used only an experimental comparison using two tracks, the demo track and the base track. And the demo track is equipped by the eco-route planner. On the contrary, the base track was not equipped with the eco-route planner. And the drivers cannot use navigator in order to change, for example, street roads, for example, when an accident occurs near Bari, because the fleet company does not allows to change roads during the mission. So the eco-route planner is important because it is an object that allows to the driver to changing routes. So for this reason, the experimental results and the experimental mission was important for the project.
Okay, thank you again. So we can proceed with the last presentation that will be given by Angel Molina Acosta. And it's related to the work titled Modeling and Control of Test Scenarios via Hybrid Automata for Validation of Autonomous Driving Functions. So, please.
Yes, hello. Thanks, Paolo.
Okay, please share the presentation.
I can see. I think it's loading.
Okay, we can see.
Okay.
Thank you. You can start.
Yes, okay. Thanks, Paolo. My name is Angel Molina. I am a student, PhD student at Chalmers University in Gothenburg, Sweden. And I am working together with Professor Paolo Falcone from Chalmers University and University of Modena as well. And we're researching on modeling and control of test scenarios for validation of autonomous driving. And our research is motivated by this setup, which is called vehicle in the loop testing, and it basically means that a function on a car is tested with a full-scale vehicle in a confined environment, like a proving ground or a test track, basically using some automated test tracks, automated test targets that are basically mobile robots that can follow a certain path. And everything is coordinated by a central server that is monitoring the position of all of the vehicles on the test track, and that specifies a certain trajectories for this mobile robot so that they move according to a specified test scenario. So then the vehicle under test, the VUT, can experience a certain traffic scenario. And what is new about our research is the type of scenarios that we are addressing, which are more challenging than the ones currently being used. Let me show here a simple example of a scenario devised to validate the autonomous overtaking function of a vehicle. So in this scenario, we have the vehicle being tested, the red vehicle, and two other targets, targets 1 and target 2. And this vehicle on the test is approaching a target 1, which is driving slower. So this VUT wants to overtake at some point. But at the same time, there is another target driving on the opposite lane. So this is a two-way road. So to make this scenario challenging for the autonomous function of the VUT, the blue test target, target 1, will try to catch up with the vehicle on the test, so that in the end, the vehicle on the test will have a limited amount of time to either complete or decide to abort the overtake. And in this way, its function can be validated. So this scenario is complex because we have to coordinate multiple test targets. And also it's not possible to just assign predefined trajectories to the targets. We have to generate those trajectories depending on what the VUT is doing. And more importantly, since we want to allow the autonomous vehicle to exhibit its autonomous function, the testing system should not control the motion of the VUT. So this means that we perhaps don't know what the future motion of the VUT will be. We might not know how fast it will drive, for example. So that makes it challenging if we want to make sure that we execute a scenario as specified by a certain protocol. So to model this type of scenarios, we are using a paradigm known as hybrid automata, which is basically a combination of discrete variable and continuous variables. So we have a discrete state that we call Q, and this one is associated to the different operating modes or stages in the scenario. So we assume we have NQ different modes. So this discrete state is basically associated to a finite state machine. But we also have the continuous dynamics. So we have a continuous state X, whose dynamics are described by some function F, and they depend on the state, control input U, and the external disturbance W that captures the states and inputs of the vehicle on the test, which are not to be controlled, but are actually controlled externally. And we also specify some additional requirements on this hybrid system. We want to satisfy constraints on the states and inputs to represent the motion capabilities of the test targets, and perhaps also safety constraints. And we assume that the disturbance, the external disturbance, is bounded. So we don't know what it will be in the future. We don't know what the states of the VUT will be in the future, but we can actually measure them at the current at every sampling instant. So we encode the different control objectives throughout the scenario or we specify the control objective as a target set in the subset of admissible states. So we want the state to be controlled to enter eventually this target set. And all of these sets are mode dependent, meaning that they can be different for the different stages in the scenario. So this graph illustrates how we conceive this a scenario as a hybrid automaton. We have the different discrete states, the different operating modes, and we have transitions occurring between modes when the state enters the specified target set. So having described this, the problem that we're trying to solve is to determine a control input that will make the discrete state Q evolve sequentially as 1, 2, 3, all the way to the last operating mode, while satisfying the mode-dependent state and input constraints. And this for all possible sequences of the bounded disturbance W. So this is a robust control problem. Okay, our control approach to solve this problem is basically to subdivide the entire problem into smaller subproblems. So in this example, we have 3 operating modes. And we have the admissible states represented by squares. So we have 3 different admissible states. We have 3 different target sets. And the idea is to control the state from an initial condition, x0, into the first target set, and from there into the next target set, and so on. And we want to do this keeping or making sure that the solution remains feasible. So we want the state to remain inside a set of feasible states from which we can control the state to reach the different target sets. So the main question here is how do we determine these feasible states if there are any? And to address that question, we propose a feasibility analysis that is based on the concept of robust controllable sets or reachable sets. And basically, we define a reachable set as for a certain set S as the states that can be controlled to enter the set S in one time step. So all the states for which there exists an admissible control input, such that the state will be controlled to enter the next set for all possible disturbances in the bounded disturbance set. So applying this definition recursively, then we can say that the Kth robust controllable set contains all states that can be controlled robustly to enter the set S in at most K steps. So borrowing this definition, we then define a set lambda I, which depends on the operating mode, which is basically the intersection of the target set with the robust controllable sets for the next target set. So let me clarify this. Basically, the set lambda I contains all states in the target set for mode I that can be controlled robustly into the next target set, and from there into the next target set. So if we analyze and verify that all of these sets lambda I are not empty for all of the operating modes in our automaton, then we know that a solution exists to the problem also if the initial condition belongs to one of those robust controllable sets for the first target set. So this feasibility analysis can be done offline if we have the specifications of the target sets and the system dynamics and constraints. And then what we want to do online is to solve a constrained optimal control problem to actually find out what is the input that will achieve or that will ensure the correct evolution of the state. So we do this well by solving a QP problem. So at every time step t, we measure the current state and the current disturbance. We assume that we can have access to those. And we have to solve an optimization problem to determine an input sequence up to a certain prediction horizon n that minimizes a certain cost function and that satisfies input constraints, and more importantly, a set constraint which ensures that the next predicted state, the state in the next time instant, will belong to the next controllable set. And well, we solve this optimization problem, and then we apply the optimal control input. So basically, what we're doing is this. We make sure that our optimization problem will keep the state inside of the robust controllable sets, inside of the chain of robust controllable sets, until we can finally reach the target set. Okay, so let me show a simple simulation example of the scenario that I introduced in the first slide. So in this simulation, we have the state vector x that collects the inter-vehicle gaps, delta x1 and delta x2, and the velocities of the test targets. The inputs, the control inputs will be the accelerations of the test targets. And here we are only modeling the longitudinal dynamics of the vehicles. And as external disturbance, we have the states of only the velocity and the acceleration of the vehicle in the tests. Those are variables that the control system is not influencing. And with this choice of states, we can represent the system as with linear dynamics with an additive disturbance if we assume some double integrator dynamics for these states. So this scenario this example scenario consists of 3 stages or 3 modes. In the first mode, targets 1 and 2 will drive within certain speed bounds, and then in mode 2, target 1 will try to stay ahead of the VUT. So this delta x1 should stay positive. And finally, in mode 3, the test targets will slow down to open a gap for the VUT to cut back in, which basically means delta x1 should now be negative and delta x2 should still be larger than some value. So this plot shows the state trajectories for the simulation of the scenario. This first plot shows the inter-vehicle gaps, delta x1 and delta x2, 1 in blue and 2 in green. And this plot shows the velocities of the vehicles, including the velocity of the VUT. Let me clarify here that the speed profile for the VUT is chosen as a predefined profile that is bounded between 15 and 20 meters per second, but this profile is not revealed to the controller except well, I mean, the controller only has access to this state to the present state, but not to future values of the speed profile. So we see that we have 3 different modes: mode 1, 2, and 3. And in mode 1, targets 1 and 2 they drive with certain speeds. Target 2 actually has to accelerate a bit to make sure that it keeps within the feasible set of states, and the VUT is driving at a constant speed, and then it starts to accelerate to try to overtake. And we see then that target 1 also tries to catch up with the VUT. So we see that during mode 2, the gap delta x1 is actually between 0 and 30 meters, meaning that the VUT is not able to overtake the blue target. And later on, when the gap between target 2 and the VUT is getting too small, then both test targets need to slow down to open a gap. And we see that by the end of mode 3, vehicle 2 is still 50 meters away from the VUT, and the vehicle 1 is already behind the VUT. So then this means that the VUT is able to cut back in safely. And just to clarify how this looks with all of these robust controllable sets, in these plots we have sort of a phase portrait of the states, delta x1 and velocity 1, and here delta x2 and velocity 2. And we see the state trajectory starting from the 20th robust controllable set for target 1. And from there, it evolves all the way into the first target set, the lambda 1, which is a subset of a robust controllable set for target set 2. So we see that the state is evolving. It's traveling through different target sets, both in for target 1 and target 2. So with this, we show that we can robustly control the states, despite the fact that we don't know what the future values of the disturbance will be. So to wrap up, we presented here an approach to model scenarios for validation of autonomous driving functions, where we don't know the future motion of the vehicle under test, or there is an externally controlled agent in the system. We propose to analyze the feasibility of such scenarios via reachability analysis. And then we proposed a constrained optimal control problem to ensure the robust execution of a test scenario. So with this, I come to the end of the presentation. Thank you for listening, and please ask any questions if you feel interested, or you can also contact us via email for sure.
Thank you, Angel. Are there any questions? If yes, you can write a message in the comment chat and book a slot for asking. I cannot see any requests. I just have one. If I understood correctly, it is assumed that the speed of the 2 other vehicles are in some way known. Is that correct?
Yes, you mean the speed of the test targets, or?
Yes.
Yes, exactly.
The test targets. So in some way, you are supposing that you are able to detect or estimate their velocity.
That is correct. Yes. With this diagram, I wanted to represent that we have access to some estimate or measurement of the states of all of the vehicles in the scenario.
So it should be part of a structured system in some way.
Exactly. Yes, we need some central server that is communicated via some wireless infrastructure to the mobile robots, which would need some sensing equipment on board, of course. Also, the vehicle in the test should have some measurement equipment on board. Yes, which is actually how, at least at Volvo Cars, where I am employed, this is how they also do tests. They can control these test targets remotely, and they have some sensing equipment on board.
So you are supposing that you should be able also to act on the target vehicles.
Exactly.
So to influence their behavior. Okay.
That's correct. Yes.
Any other questions? I think not. So it was the last presentation, and I think that we can close the session. We are perfectly on time. I would like to thank all the speakers for their contributions and presentations, and also the participants to the session for their interest in the presentation. So thank you again, and so let us continue on the squares, and thank you again, and bye.